The last thing I want to talk about here is kind of trying to tie everything back together. So, what does all this mean or do? And when I'm talking about this, I'll probably pick one specific example to think about. But real quick, I just want to sketch a couple different things. So, we've talked a lot about stuff to calculate from R of t. And you can kind of think about R of t a lot of different ways. So maybe you imagine just R of t describing some wonky curve in space. So R of t is just any series of functions. That's kind of how we first learned to deal with it. But especially thinking about the fact that you all are creating paths and writing word problems for your project, some common examples could be like, here's the sun. Here's a very exaggerated orbit. And here's us on a planet or whatever. And movement around on that orbit, you could say, is like approximated by an ellipse. Oops. I don't know, a sine theta t, b cosine phi t. Not really sure what that r would be, but something like that. You could imagine you write the shape you want, you write the r that matches it. You could work with an r of t like that and do all the things we're about to talk about. That example that we did in section 10.2, where there was the cliff and the ball that got thrown off the cliff, our first principles from physics, F equals ma, can give us some r of t. Or you could be like, oh, here's one. So here's like a slide, like at a park that somebody could want to go down, I guess, just for fun. Ooh, everything's lagging on my end, sorry. Those are stairs going up the slide. Here's the actual slide. I don't know. Somebody's at the top. Maybe they roll a ball down or they go down themselves. Who knows? But that's a slide, and you could say, oh, well, if I wanted to plot it, this is the one we'll go ahead with. That looks kind of like y equals 1 over x. I know I can look at something flat, write y equals 1 over x. So maybe I could write this in those special vector forms that we've learned recently. So any of these examples, you can do arc length, curvature, any type of question with it. I'm going to work with this one right here. Just because this abstraction y equals 1 over x, this kind of idea is one I don't think we've done examples with in this section yet, so may as well do that. So let's say for whatever reason you've decided you really care about that picture of a curve, y equals 1 over x. And the scenario I've invented where you care about the curve y equals 1 over x is you are trying to write a word problem about a thing going down a slide. This is about the shape of a slide, so you've decided that's what matters. Everything we've done is in terms of r of t. So first of all, how do we bridge the difference between there's this whole class of things we can write in the xy plane? How do we move it over to vectors? That's really easy. Remember, r is just a vector that tells us x, y, and z. R of t should have those things depend on t in each component. And so if I know that y is 1 over x, that's the information I have. I can go ahead and recast everything in terms of t. So I can say y is 1 over t, but that just means that x is t. 0 doesn't matter. I'm doing nothing with 0. So going down the slide, uses position vector or vector function r equal to t 1 over t. So that's the quick jump in reasoning you can use to go from a picture of a shape with a function to something in terms of vectors that we can practice all these new skills with. And then let's think about all the different types of questions you could write, like for a word problem. The first thing in this section we talked about was computing those tangent vectors and normal vectors. And remember that gave us our formula for arc length. But if we remember back to the pictures that showed us what tangent vectors really mean, tangent was a derivative. So questions about the tangent vector can be related to speed or velocity if you maintain the vector, speed if you take the magnitude. Arc length was kind of finding the measure going around a curve, also integrating that derivative speed. So this is about distance traveled. So you could ask yourself, how fast is the kid or ball? And we'll do kid going down the slide. And then since you know your position vector is t 1 over t, we can write that as t to the minus 1 for easy derivatives. R prime of t is going to be 1 minus t to the minus 2. And so speed is magnitude of r prime of t, going to be square root 1 squared plus minus t to the minus 2 power squared. That's square root 1 plus t to the minus 4, square root 1 plus 1 over t to the 4th if you want to write it that way. And so you could plug in any time t and figure out how fast you're going down the slide. As you plug in bigger and bigger t, this last part gets smaller. So kind of it makes sense. The fastest part of the slide is right at the start, at the steep part, and then kind of it starts to level off and you start moving more slowly at the end. We haven't uncovered anything amazing here, but it matches our intuition. For arc length, you could do if kid is on slide for 3 seconds, how long is the slide? Physically long. And then length, that should get you thinking this is an arc length problem. So I think we denoted arc length by s. That should be the integral for however long you're thinking about in time. So from 0 to 3, magnitude of r prime of t dt. How long is the path? Integral from 0 to t, square root of that 1 plus 1 over t to the fourth. We just found a second integrated with respect to t. You compute a number. And again, I'm talking about the slide example, but you could go back to any of yours.